In this topic, we are discussing about kinetic theory of gas. Before that, subscribe, share, and like our videos. Let's continue the topic, kinetic theory of gas. Before we derive an equation, first let's see some assumptions related with a kinetic theory of gas. These assumptions, first, any calculation related with temperature must be in Kelvin. It must be in Kelvin. And there are 5 assumptions. These assumptions made in kinetic theory of gas. Kinetic theory of gas. The first assumption is the internal energy is made up of random kinetic energy, which means there is no potential energy component. And the second assumption were in assumptions made in kinetic theory of gas is collision between particles and particles and the wall, and the wall is perfectly elastic, The third assumptions made in kinetic theory of gas is the volume of a particle is negligible compared to the volume of a gas as a whole. And the fourth assumption, the distribution of the velocity of a particle is random. And the fifth assumption, Newton's law can be applied for any collision. Using this assumption and using some mathematical analysis, we can derive some equations that explain kinetic theory of gas. Consider a block which is a cube with length L, width and height equal, and it consists of a number of particles. It consists of a number of particles, and the total number of particles n is given by number of mole times Avogadro's number. From this number of particles, let's take a single particle which is moving along the x-axis. So let's take x-axis, y-axis and z-axis. A particle with mass m and velocity v, which is moving along the x-axis. Then it collides with a shaded part of a cube. When it collides with a shaded part of a cube, there is a change in momentum, and this change in momentum delta P equals mass times change in velocity v. Since the collision between particles and the wall, and between particles and the wall is perfectly elastic, the particle will rebound with the velocity v. Hence, the momentum delta P equals m into twice a velocity v, because change in velocity is the difference in the velocity of the final velocity and the initial velocity. When we rearrange this, we get 2 times mass times velocity. This is a change in momentum delta P. This is our equation 1. And time for 2 successive collision, time for 2 successive collision is equal to time t equals delta L over v. This is from time t is equal to distance over velocity v. Distance in this case for successive collision equals twice L. Therefore, instead of S, we can use twice L over velocity v. This is our equation 2. From the 5th assumptions made in kinetic theory, the 5th assumption says that Newton's law can be applied for any collision. From this, from Newton's second laws of motion, force F equals change in momentum over time. The time rate of change in momentum, which is equal to force. This is from Newton's second law. Newton's second law. And from equation 1 and equation 2, change in momentum equals twice mass times velocity and time twice L over v. This is from equation 1 and equation 2. Now cancel 2 by 2 and V, since it's a ratio, raised, and we get force F is equal to 2 by 2 mass times V squared twice mass times speed squared over length L. This is our equation 3. Now we are taking a single particle, but there are n number of particles in a cube. Hence, the total force F equals total number of particles we multiply by the total number of particles n mass times V mean squared over L, where V with bar square means it is a mean square velocity. Mean square velocity, because the velocity of a particle is random, so we are taking a mean square velocity, and the mean square velocity is equal to the velocity of a particle plus the velocity of the second particle square plus, since we have n number of particles, the velocity of the nth particle square divided by the total number equals a mean square velocity. And also the particles are in random motion, so there are 3 freedom of motions. They can move along the x-axis, they can move along the y-axis, and can move along the z-axis. Therefore, force along the x-axis equals 1/3 of the total, because they can move along the x-axis, y, z, 3 freedom of motion. The force along the x-axis is equal to 1/3 of the force, which is 1/3 n times mass times mean speed squared over length L. And from mechanics, we have that a pressure P is equal to force acting per unit area A, and force from equation 4, force F is equal to 1/3 total number of particles mass times mean speed squared over L, and area, since it is a cube, area of the base equals L squared. Therefore, a pressure P equals 1/3 total number of particles mass times mean speed squared over L squared times L, which is L cubed, and pressure P equals 1/3 total number of particles mass mean speed squared over L cubed, the volume of a cube, which is equal to volume V, and pressure P times volume V is equal to 1/3 volume, let's take to the right, to the left, equals 1/3 n times mass times mean speed squared. This is our equation 5. Equation 5. Now using equation 5, which is pressure times volume V is equal to 1/3 total number of particles mass times mean speed square. And from equation of state, which is pressure times volume V equals number of mole times a universal gas constant times temperature T. And from the total number of particles N is equal to number of mole times Avogadro's number, where this is the total number of particles in a cube. N is equal to total number of N number of mole times Avogadro's number. Now solve for a number of mole. N is equal to total number of particles over Na, which is Avogadro's number. And pressure P times volume V equals, instead of N, total number of particles over Avogadro's number times the universal gas constant times temperature T. Here there are two constants. These are a universal gas constant R and Na, which is Avogadro's number, where R equals 8.31 and Na equals 6.02 times 10 to the power of 23. The ratio of these two constants, R over Na, which is equal to a new constant, which is a Boltzmann constant. And when we take the ratio, we get 1.38 times 10 to the power of minus 23. Therefore, pressure times volume V equals number of particles times a Boltzmann constant times temperature T. This is our equation 6. Now, compare equation 5 and equation 6. Compare equation 5 and 6. Equation 5, pressure times volume is equal to NKBT. And equation 5, pressure times volume is equal to 1/3 total number of particles mass times mean speed squared. When you compare, we get N Boltzmann constant times temperature T equals 1/3 total number of particles mass times mean speed squared. N cancel N, Boltzmann constant times temperature T equals 1/3 mass times mean speed squared. Now, write out the equation by 2/2, which is 1. Any number multiplied by 1, the number itself, and using commutative property of multiplication, we can write this equation as Boltzmann constant times temperature T equals, let's move 2 to the left and 3 here, therefore 2/3 into 1/2 mass times mean speed square velocity. The quantity under the bracket, which is kinetic energy, therefore a Boltzmann constant times temperature T equals 2/3 times a kinetic energy. Again, multiplied both sides of the equation by 3/2 by 3/2. 2 cancel 2, 3 cancel 3. Then we get a basic equation. Kinetic energy equals 3/2 Boltzmann constant times temperature T. That is why kinetic temperature is a measure of average kinetic energy of a particle in a substance. This indicates that temperature is a measure of average molecular kinetic energy of a particles. That is why we say this. And also from mechanics, kinetic energy equals 1/2 mass times a mean speed square. From kinetic theory of gas, kinetic energy is equal to 3/2 Boltzmann constant times temperature T. Now solve for a mean square velocity, 2/2, then mass times a mean speed squared equals 3 times Boltzmann constant times temperature T over mass m cancel. Therefore, a mean speed square is equal to m, or a mean speed equals and radical 3 Boltzmann constant times temperature T over mass m. This shows that again, this shows velocity and temperature T is directly proportional to a mean speed square. Temperature is, because if we squaring both sides, mean speed square equals temperature, and this shows that temperature is directly proportional to the square of velocity v. And solve for a pressure, divide by volume v, cancel, then pressure P equals 1/3 total number of particle mass over volume density times a mean speed square velocity. For n equals 1, we can write this pressure P equals 1/3 density times a mean speed square. We have this. A pressure equals 1/3 density times mean speed square. This is what we have under kinetic theory of gas. Next we'll see examples related on it, and Dalton's loss of partial pressure, Ram's loss of diffusion. Until there, goodbye.